Hello, I'm Robert Hawkins, and I'm excited to present some work on the use of large language models in cognitive science that I've done over a period of delightful collaboration with Taka Yamakoshi at the University of Tokyo. Great. So world knowledge plays a crucial role in language understanding, even if it's not clearly mentioned in the literal propositional meaning of a sentence. Okay, so for example, when we hear a sentence like the fish ate the worm, we of course imagine a fish and a worm. We know that they have certain properties, like fish have eyes and scales, worms are slimy, and fish like to eat them. So, these are entities that we plug into our semantic knowledge. And then there's attributes of the situation itself. So we may understand that after being eaten, the worm is probably not going to exist anymore. It's inside the fish. And the whole situation likely happened in a body of water because that's where fish live. So in this way, as we hear a sentence, there's a very classic account of what happens as we incrementally process the sentence and dynamically construct this schema known as a situation model. And the situation model is supposed to capture all of the kind of extra linguistic world knowledge that we bring into the interpretation of a sentence and all of the kind of implications we can draw from a sentence, even when they're unspoken. So in this work, which we presented earlier this summer at the ACL conference, we were interested in the extent to which large language models construct situation models like humans do. And if they do, what is going on under the hood that allows them to do so? And we hope that this may give us some insights into the kind of process level, representation level accounts of how a distributed system like a large neural network may kind of have these emergent properties that allow them to do common sense language understanding. And if it's all smoke and mirrors and they're relying on other kind of heuristic cues, we would like to understand that as well. So how do we do this? Well, in order to test the ability to construct situation models, we operationalize this in a classic task known as the Winograd schema challenge. So Winograd schemas are pairs of sentences, like Paul tried to call George, but blank was not successful, where the question is, do you fill the blank with Paul or with George? And they come in these pairs where a single context cue, here in orange, successful or available, flips the prediction. So it's this very minimal modification to a sentence that dramatically changes the interpretation of a pronoun. So essentially, but he was not available. So there's a bunch of different ways that you can evaluate performance in a task like this, but we wanted to use a fairly strict one. So we required, in order to say that the model got it correct, it had to assign the correct response higher probability than the incorrect response in both sentences. So it had to think that Paul was better than George for the first sentence, and that George was better than Paul in the second sentence. So here's what we found. Humans are unsurprisingly very good at this, achieving over 90% accuracy. Large language models are less good overall. So this is a very strict metric. So, Albert getting up to 30% or so certainly is more impressive than a lot of the previous generations of models could do, because the accuracy is essentially 0% for chance, because you have to get both in the right direction. So these are all of the open source models we tested. We also looked at some models that are restricted behind an API, so we can't actually reach in and play with their weights. So we use GPT-4 and GPT-4 with some fancy chain of thought prompting, and find that you can really push up performance on this curve that looks like at some points it will reach human level performance on this task. So what we see here is a increasing curve where there seems to be some improvement at the ability to do this fairly challenging task that requires some amount of very heterogeneous world knowledge in order to predict the correct referent of the pronoun. So we picked out the best open source model that we were able to explore. And even though it's not as good as these more recent models, we think that it still gives us some insight into the kind of first glimmers of performance at this inflection point of the curve. And as increasingly powerful models come out, we can, of course, extend this analysis to those. Okay, so we wanted to contrast this context task where purportedly these are constructed so that you can't make a prediction on the basis of any other literal information in the sentence. You need to use something about a world model. So we constructed for each pair of sentences in the Winograd schema a corresponding verb manipulation sentence that was possible to solve only using an agreement queue on this auxiliary verb after the mask. So the idea here is to disentangle the circuits of the model that might be responsible for world knowledge as opposed to other kind of generic pronoun disambiguation competency. And kind of comfortingly, we found that even the pretty small models are good at this agreement task. So that also gives us some confidence that there's something in the Winograd schemas that really is drawing on different machinery. So in order to look at this more systematically, we used this approach that we got really excited about from Atticus Geiger at Stanford called a causal interchange intervention. So a causal interchange intervention essentially reaches in and surgically swaps out representations at a specific token and layer with what they counterfactually would have been for a different sentence. So this allows us to test whether that representation at that very local site played a causal role in the model's eventual prediction. So we basically zap at a particular token and then use this odds ratio to measure how much it interfered with performance. So in this case, we first started out with these layer-wise interventions. So we're essentially zapping every single head at a layer and look at how this affects it at each token. So this allows us to look at how information gets propagated across tokens as you move up layers. And just as an example, here's one sentence, and the effects are shown in red going horizontally across layers for different tokens. So just as a sanity check to orient you, the word available is the only word that's different across these two sentences. So if you swap out the representation at that location, even early on, you're essentially using the other sentence, right, at the first layer. So unsurprisingly, there's a very large effect consistently across layers at the kind of source of the difference. What's more interesting is these effects that emerge at other locations in the sentence. For example, at the options, Paul and George, and the kind of construction, the tried to call construction that they're embedded in, as well as this kind of comma token, which is consistent with earlier evidence showing that large language models use these kinds of tokens to pool information across larger constituent phrases. Okay. Importantly, this looks pretty different for the verb manipulation. So it looks like much of this distributed kind of information flow through the rest of the sentence is kind of truncated, and you're mostly getting effects at directly from the place that the verb cue is available to the mask where you're making a prediction, and not as strong elsewhere. So looking at this more systematically across many, many sentences that have, their masks and different kinds of context in different places, we see a curve like this, where there are effects of intervening outside the context that start to arise around layer 7 or 8 in the context condition. And then you get these big effects at the options, the Paul and George tokens, that you just don't get in the syntax condition. So it appears that the syntax condition is using a more direct propagation, where the mask is able to just look at the verb to know what it has to do, whereas in Winograd schemas, it has to pool information in some more complex way. Okay, so that's the layer-wise invention. The last thing I'm going to show you is the ability to go a little more fine-grained with these interchange interventions. So you can not just zap an entire layers representation, you can actually go into the individual attention heads, okay, and ask what those attention heads might be contributing toward the kind of mechanics of propagating this information from site to site. So we found extremely localized circuits going through particular heads. So this is a head that essentially transmits information from the context to the rest. And you can see this because if you zap the information being exported at the context token, you get the same effect as the output at the zapping the output of this head at the rest of the sentence tokens. And we find other heads that perform similar kinds of operations on different kind of information pathways. So there's a head that seems to propagate information from context to rest. There's a couple heads that go from kind of these places where information is pooled to the options. And then there's one head at the very end that the mask uses to decide which option to attend to, and then copies that one over to make its final decision. So we were really excited about this method. Obviously, it's deployed here for a very kind of specific problem, but it allowed us to really identify this fairly local circuit that is kind of algorithmically giving rise to these predictions in a way that's not simply relying on lexical cues. So when you look at this circuit for verb cues, it looks really different. So it is much more direct from the verb to the mask without going through all this additional kind of pooling and integration. Okay, so as a kind of final treat, I wanted to mention a data set that we have made available looking at the kind of subtle gradient effects of different verb biases. So this is another kind of instance where there's an interesting interaction between a lexical item that has information about the constructions that appear syntactically. So we found that if you compare across all of these different models, the really big large language models, in this case, BERT was the biggest one that we tested, do a really good job, not just of capturing kind of discrete binary judgments about syntax, but also very graded sensitivity to the kind of semantics of the construction and the lexical content that drives that preference. Okay, so to wrap up, we first of all have found that large language models, just in terms of their performance, when you test them in these more kind of targeted ways, are beginning to show human-like gradient effects and glimmers of what might look on the surface like a human-like situation model. We wanted to kind of push this technique of causal intervention analyses as a way to treat a language model like a kind of sandbox of kind of algorithmic probing, where you can actually map out these neural circuits that give rise to a particular behavior of interest. And finally, I think there's kind of an exciting piece of evidence here that there are distinct circuits kind of localized in different attention heads that kind of handle semantic information versus syntactic information, which may suggest that these are kind of disentangled representations that require different processing, which I think has very interesting implications for our cognitive models. So with that, I want to thank my collaborators, especially Taka, who led all of the work that I've talked about.